Imagine looking into a perfect mirror, but instead of just reflecting light, the glass reveals an entirely physical, parallel universe. In this bizarre mirror world, everything looks exactly the same, but the fundamental charges of reality are completely flipped backward. Now imagine that if you were to reach out and touch your reflection, both you and the mirror would violently annihilate in a blinding flash of pure gamma radiation, converting your entire mass into pure explosive energy. For the brilliant physicists of the early 20th century, the universe was supposed to be simple, stable, and safe. Everyone comfortably agreed that all of physical creation was built from just two basic, predictable puzzle pieces: the heavy, positive proton, and the lightweight, negative electron. The concept of a shadow world made of antimatter sounded like absolute lunacy, a concept reserved for cheap pulp science fiction, not rigorous laboratory science. But in 1928, a quiet, eccentric theoretical physicist named Paul Dirac was staring at a chalkboard, trying to mathematically marry the strange new rules of quantum mechanics with Albert Einstein's theory of relativity. When Dirac finally solved his ultimate equation, he realized a bizarre quirk. His formula had two distinct answers. Much like how the square root of 4 can be either a positive 2 or a negative 2, Dirac's math explicitly demanded that an entirely mirrored, negative energy twin of the electron must physically exist somewhere in the cosmos. Most scientists fiercely dismissed this mathematical glitch as a mere illusion. After all, if this phantom matter was real, why hadn't anyone ever seen it? In 1929, Russian physicist Dmitry Skobeltsyn unknowingly stumbled upon this mirrored reality with the aid of a customized cloud chamber. Skobeltsyn placed his gas-filled chamber inside a powerful magnetic field to study high-energy cosmic rays raining down from the sky. He tried to calculate the momentum of these invisible cosmic bullets by observing how the magnet forced their ghostly vapor tracks to curve. While taking into account the standard, predictable behavior of regular electrons, Skobeltsyn noticed something completely inexplicable. A few rare tracks curved in the exact opposite direction, behaving exactly like electrons, but somehow carrying a positive charge. However, unable to reconcile this with the stubbornly accepted laws of physics, he conservatively assumed they were just regular electrons traveling perfectly backward, leaving the definitive physical proof of antimatter a frustratingly elusive mystery. This theoretical debate would rage on for another few years. But the first true, undeniable evidence of antimatter would come in 1932, when an American physicist would have a brilliant burst of experimental intuition that would finally prove the existence of Dirac's phantom particle. Carl Anderson was born in New York City in 1905. Little is known about Anderson's early life other than the fact that he enrolled in Caltech and quickly distinguished himself as an incredibly gifted experimentalist. His mentor at Caltech was none other than Robert Millikan, the famous physicist who first measured the charge of the electron. In fact, Millikan had tasked Anderson with studying the extreme energy spectrum of cosmic rays, and therefore Anderson had the opportunity to build the most advanced radiation detection equipment on the planet. In 1930, Anderson began constructing a massive cloud chamber to track these high-speed particles. He spent months perfecting the device, surrounding it with a colossal 4-ton electromagnet to forcefully bend the paths of the cosmic rays. After making hundreds of photographic observations of the particle tracks, he noticed the same peculiar phenomenon Skobeltsyn had seen. Anderson had been tracing the curvature of these lines to measure the energy of the particles, and noticed that some tracks were bending exactly like an electron, but in a direction that indicated a positive charge. Anderson could come to two main conclusions after observing this phenomenon. The first was that the particle was just a regular proton, behaving slightly strangely due to extreme cosmic velocities. The second was that he had discovered a brand new particle, an exact twin of the electron, but with a positive charge. To try and figure out which of the two possibilities was correct, Anderson had to definitively prove the direction the particle was traveling. Later that year, he ingeniously placed a 6mm thick plate of solid lead directly in the center of his cloud chamber. When a high-speed particle hits the lead, it loses energy and slows down. Because slower particles are bent much tighter by a magnetic field, the track coming out of the lead would have a much sharper curve than the track going in. So, Anderson just needed to capture a photograph of one of these mysterious positive tracks passing through the lead plate to definitively see its speed drop, proving its direction of travel once and for all. Anderson finally captured this golden event on film, finding the particle was traveling upwards from below the chamber. Combining this upward direction with the known strength of the magnetic field, Anderson could accurately calculate the particle's mass. Because a massive proton would barely be deflected by the magnet, Anderson concluded that this particle was infinitely lighter, exactly the same mass as a normal electron. This new particle is what we now know as the positron. Most of the initial skepticism regarding Anderson's discovery was attributed to two correlated assumptions. The first was that no one understood how an antiparticle could survive on Earth without instantly annihilating. The second was the extreme mathematical discomfort of confirming Dirac's wild, negative energy theories, which many veteran physicists still simply refused to believe. Anderson published his groundbreaking results in a short paper entitled The Positive Electron the very next year, in 1933. Almost immediately after Anderson's work brought to light the first experimental evidence of antimatter, English physicist Patrick Blackett and Italian physicist Giuseppe Occhialini refined the discovery even further using an entirely different method, a triggered cloud chamber. Blackett's intention was not just to find random positrons, but rather to find evidence of how they were being created in the first place. Blackett figured that if he were to attach Geiger counters above and below the chamber to trigger the camera only when a cosmic ray passed perfectly through it, it would drastically validate the frequency and origin of these particles. Anderson himself had taken thousands of random photos to find just a few hits, an incredibly slow and tedious process. Blackett and Occhialini were indeed able to capture spectacular images, uncovering a completely different phenomenon: explosive showers of multiple particles erupting from a single point. With some genius insight, they determined that these strange bursts were actually pure energy spontaneously converting into matter, creating both an electron and a positron at the exact same time. When a high-energy gamma ray strikes a heavy nucleus, it literally spawns a particle and its exact antimatter twin. The discovery of this pair production not only provided the first direct evidence that Einstein's famous equation worked in reverse, but also definitively proved Paul Dirac's mathematical theories were a physical reality. The evidence provided by Blackett was crucial in determining that antimatter is fundamentally woven into the fabric of physics. There was still a profound desire to hunt down the rest of the antimatter family, led mainly by physicists who knew that if the anti-electron existed, the antiproton must exist as well. But finding an antiproton was vastly more difficult. Because a proton is 2,000 times heavier than an electron, creating its antimatter twin would require 2,000 times more energy. Up until this point, all of the discoveries of antimatter had been made through passive observations of random cosmic rays from space. No one had yet successfully created heavy antimatter on demand, for no one had a strong enough particle accelerator, or if they did, they didn't have the technology to manifest that massive energy requirement into reality. Once the first theoretical limits of pair production were understood, though, many scientists realized to what degree of immense violence they were working with regarding antiprotons, and therefore realized the grand scale at which they needed to make an experimental apparatus. American physicists Emilio Segre and Owen Chamberlain were the first to successfully use such a colossal machine, and subsequently discover the antiproton based off of high-energy collisions. Their 1955 setup went as follows. They used the massive Bevatron accelerator at Berkeley, which was specifically built to reach billions of electron volts. They directed a beam of protons moving at near the speed of light into a copper target. They then set up a complex array of magnetic lenses and timing detectors to filter out the resulting explosion of debris. The newly spawned antiprotons would be seen only if they had the exact specific momentum and negative charge required to perfectly bend through the 40-foot magnetic labyrinth to reach the final detector. Segre and Chamberlain then analyzed the precise velocity and mass of the particles that made it through. Their calculations yielded an undeniable confirmation. They had captured the massive, negatively charged mirror image of the proton. Interestingly enough, at almost the exact same time, other physicists were completely shifting the goalposts of antimatter research from just finding particles to trying to build entire antimatter atoms. This next monumental leap would take decades of technological evolution. The theoretical setup also included combining antiprotons and positrons, but in this case, the device wasn't a particle accelerator blasting things apart, but rather a particle decelerator trying to gently bring them together. Antimatter naturally annihilates in a flash of gamma rays the exact microsecond it touches regular matter. Knowing the incredible difficulty of trapping something that explodes on contact, physicists had to design ultra-high vacuum magnetic bottles to hold the antimatter perfectly suspended in nothingness. Most of the creations of antimatter up to this point have been chaotic, high-energy flashes that vanished instantly, but they have not been stable. Most of the particles degraded in fractions of a second. Freezing antimatter in place to study it would require much more precision. This technology would not come until the late 1990s, and would come at the hands of massive international teams working at CERN in Geneva, Switzerland. The Athena and Alpha experiments at CERN are known more famously for their incredible breakthroughs in capturing entirely complete antihydrogen atoms. It is the most sophisticated containment experiment in all of physics, and provided strong evidence that the fundamental laws of light and atomic structure are perfectly mirrored in the antimatter universe. The Alpha experiment itself operated through supercooling antiprotons and positrons to near absolute zero. CERN physicists were pioneers in precision magnetic traps and had been brainstorming ways to force these antiparticles into a gentle orbit since the early days of the low-energy antiproton ring. They started with trying to find ways to slow the particles down by passing them through ultra-thin foils and capturing them in super-chilled electromagnetic wells. In 1995, they successfully created the first antihydrogen atoms, but they hit the walls and annihilated instantly. Still, even with this brief success, the scientific community was not fully satisfied. 16 years later, in 2011, the Alpha team achieved the ultimate milestone. By meticulously tuning an incredibly complex octupole magnetic field, they managed to trap antihydrogen atoms for over 16 solid minutes. Still using the fundamental principles of electromagnetism harnessed by Anderson and Segre decades prior, and with the help of laser spectroscopy, they measured the internal energy shifts of the antimatter atom. They found its behavior perfectly identical to regular hydrogen, down to an error rate of mere parts per trillion. Today, the existence of antimatter is an undisputed pillar of particle physics, and its applications have completely revolutionized modern medicine through devices like the PET scanner, which literally uses positrons to map the human brain. This means that today, studying antimatter does not just satisfy our curiosity about the subatomic mirror world, but rather pushes the absolute boundaries of why our universe even exists. According to the Big Bang Theory, matter and antimatter should have been created in perfectly equal amounts, perfectly destroying each other, leaving absolutely nothing behind. Yet, we are here. Antimatter is our universal shadow, and understanding its subtle differences is a prime example of pushing quantum mechanics to its ultimate limits. The sheer fact that scientists in the early 20th century were able to take what seemed like an impossible mathematical anomaly before and turn it into a trapped, fully formed anti-world is beyond remarkable. Thanks to nearly a century's worth of innovation and the work of many brilliant physicists, our understanding of reality's mirror has grown significantly, along with the fundamental mysteries that still lie within our universe.
The TikTok for smart people.
This video is brought to you by the Deepstash app.
Try it today.